Have you ever thought that just by looking at something, you could completely change what it is? In our everyday world, that sounds like science fiction, right? But down in the bizarre, fascinating world of quantum mechanics, it's not just possible, it's the fundamental rule of the game. So let's dive into why the simple act of observation can literally alter reality. Think about it. If you walk into a room and look at a chair, the chair doesn't suddenly change color. Your observation is passive. It's no big deal. But at the quantum level, oh, it's a completely different story. When you measure a quantum particle, you're not just gently reading some information that was already sitting there. Nope, you are actively barging in and forcing that particle to pick a side. So this is the big mystery, isn't it? Why? Why is the quantum world so sensitive? Why has the universe set up this rule that says to learn anything, you have to fundamentally disturb the very thing you're trying to understand? Well, let's dig in and find out. Okay, so our first stop on this tour is an idea that pretty much tells our common sense to take a hike. In the quantum realm, you don't just find an answer, you actually help create it. Okay, picture this. You've got a friend who is totally, genuinely undecided about lunch. Pizza, tacos, they have no idea. The moment you ask, okay, so which is it? You force them to commit. Before your question, there was no single answer. The question itself made one exist. And believe it or not, a quantum particle is a lot like that indecisive friend. All right, so if the particle doesn't have a definite answer before we ask, what is it doing? This brings us to the before and after of a quantum measurement, and it involves two of the most famous and two of the absolute weirdest ideas in all of science. The before state is what we call superposition. And I really want you to focus on that word genuinely. This is not a case of us just not knowing what the particle is up to. The particle, in a very real way, is doing all of the possible things at once. It's spinning clockwise and counterclockwise. It's here and there, all at the same time. Here's a beautiful way to wrap your head around it. Think about a musical chord. When a piano plays a C major chord, you're not hearing a C that's just hiding an E and a G somewhere. You are hearing all three notes, C, E, and G, vibrating together as one single, richer, more complex sound. That's superposition. All of these possibilities existing together in harmony. But then, we come along and measure it, and bam, the music stops. The act of measurement is like slamming your hand on the piano keys, silencing everything except one single note. We call this the collapse. That beautiful, rich chord of possibilities is gone, and we're left with just one definite reality. It's kind of like a jury. They might start out with a dozen different opinions, but when they deliver the verdict, it has to be one single thing, guilty or not guilty. All that previous uncertainty just vanishes. So we know that looking at something forces a choice, collapsing a whole cloud of maybes into one single is. But this whole process isn't just total chaos. Nature has some very, very strict rules about how this game is played. Let's break down the big three. First, you can never be 100% sure of the outcome. You can only know the odds. Think of it like a weighted coin that you know will land on heads 70% of the time. Second, the type of question you ask directly determines the type of answer you get. And third, and this one is a real mind bender, some questions are mutually exclusive. Answering one makes it impossible to know the answer to the other. And that third rule, well, that leads us right to the legendary uncertainty principle. It's a fundamental trade-off that's just baked into the fabric of reality. Imagine trying to take a picture of a race car. If you want a super sharp photo to know its exact position, you have to use a fast shutter speed, right? But that blurs all the motion, so you have no idea how fast it was going. If you want to capture the speed with a long motion blur, well, now the car is just a streak and you can't tell where it was. You simply cannot have both perfectly at the same time. And the rules get even stranger. This one is really profound. It's called the no cloning theorem. I mean, think about it. We copy digital files all day long without a second thought. But in the quantum world, no can do. Making a perfect, identical copy of an unknown quantum state is physically impossible. And it's not that our technology isn't good enough yet. It is literally against the laws of nature. So here's why that matters. Since measuring a state changes it, you only get one shot. You can't just make a backup, measure the copy, and leave the original alone. It's like having a book in a library that permanently rewrites itself the moment you read it. You'd have to be incredibly careful about how and when you chose to open that book, wouldn't you? Okay, so up until now, we've been talking about a scientist in a lab carefully deciding to make a measurement. But what happens if a measurement happens by accident? Well, that's when we meet the primary villain in the story of quantum computing, a nasty little thing called decoherence. Decoherence is basically the universe measuring your system without your permission. A stray bit of heat, a tiny vibration, a random magnetic field, any unwanted little nudge from the outside world can collapse that delicate superposition. The analogy of hearing a whisper in a concert hall is perfect. All that quantum potential is the whisper, and the environment is a noisy, coughing crowd. One little disturbance, and the information is lost forever. And this table really spells out the difference. A deliberate measurement is like a surgeon's scalpel. It's controlled, it's purposeful, and you get useful information from it. Decoherence, on the other hand, is like spilling water all over your work. It's accidental, it's uncontrolled, and it just makes a destructive mess, losing information. And this is why decoherence is such a huge deal. The entire magic of quantum computers relies on maintaining those fragile superpositions. Decoherence is the enemy that is constantly trying to destroy them. That analogy of writing on a whiteboard made of melting ice, it is spot on. You are in a desperate race against time to finish your calculation before your entire workspace melts into a useless puddle. So, with all these bizarre rules and a constant enemy like decoherence, you might be thinking, wow, this sounds completely impossible. And that's a fair thought. But this is where science and human ingenuity get really, really clever. Instead of trying to fight the rules of nature, we figured out brilliant ways to work with them. One of the most powerful tricks up our sleeve is quantum error correction. The basic idea is just redundancy. You know, if you send a really important text, you might send it twice to make sure it gets through. Quantum error correction is like that on steroids. It smartly spreads one piece of information across several quantum bits or qubits. Then it can check on the relationships between them to see if an error has occurred, without ever looking at and collapsing the actual data. It's absolutely genius. And then there's this other incredible technique called a weak measurement. It's a way to gently, peek at a system. The analogy of weighing a sleeping baby is perfect. A strong measurement would be picking the baby up and putting it on a scale. Sure, you get the weight, but you woke the baby. A weak measurement is more like gently pressing on the mattress next to it. One little press tells you almost nothing. But if you do it hundreds of times and average the results, you can get a surprisingly accurate idea of the baby's weight, all while it snoozes away. Okay, let's just quickly pull it all together. What have we learned? First, at the quantum scale, looking changes everything. Period. Second, particles exist in this fuzzy cloud of possibilities called superposition, and measurement forces them to pick just one. Third, decoherence, unwanted measurement from the environment, is the absolute #1 enemy of quantum computing. And finally, and this is the hopeful part, scientists are finding these amazing, clever ways to work within nature's strange rules, not against them. And maybe that's the most important takeaway of all. These fundamental limits of quantum mechanics, they aren't roadblocks. They're actually a map. They're showing us the challenges, the dead ends, but also the pathways to success. By understanding exactly what we can't do, we learn precisely what we must do to build the future of quantum technology. The only question left is, where is that map going to lead us next?